Process description and control loops for a slug catcher. Overview. A slug catcher is a critical component in onshore oil and gas facilities, designed to manage the intermittent flow of large volumes of liquid, slugs, and gas arriving from multiple well clusters. It ensures smooth downstream processing by separating and temporarily storing these slugs. The slug catcher also helps protect downstream equipment from damage caused by irregular flow and pressure surges. Process description. One inlet section, function, receives the multiphase flow from multiple well clusters. Components, inlet manifold, flow lines, valves. 2 separation section, function, separates the incoming flow into gas, oil, and water phases. Components, separator vessels or finger-type slug catchers, demister pads, baffles. 3. Gas outlunction, directs separated gas to the gas processing unit or flare system. Components, gas outlet line, pressure control valves, gas flow meters. 4. Liquid outlet, directs separated oil and water to their respective processing units. Components, liquid outlet lines, level control valves, oil and water flow meters, storage tanks. Basic control loops. 1. Inlet flow control, FIC, flow indication control. Purpose, regulate the flow rate of the incoming multiphase flow to ensure the slug catcher operates within its design capacity. Components, flow meters, control valves, flow controllers. 2. Gas pressure control, PIC, pressure indication control. Purpose, maintain the gas pressure within the slug catcher to prevent overpressurization. Components, pressure transmitters, pressure control valves, pressure controllers. 3. Liquid level control, LIC, level indication control. Purpose, maintain the liquid level in the slug catcher to ensure effective separation and prevent overflow. Components, level transmitters, level control valves, level controllers. 4. Gas flow control, FIC, flow indication control. Purpose, control the flow rate of the separated gas to downstream processing or flaring. Components, gas flow meters, control valves, flow controllers. 5. Oil and water flow control, SE, flow indication control. Purpose, control the flow rate of separated oil and water to their respective processing units or storage tanks. Components, oil and water flow meters, control valves, flow controllers. Operational parameters. 1. Inlet flow rate, monitor and control to prevent overloading the slug catcher. 2. Gas pressure, maintain within safe operating limits to avoid equipment damage. 3. Liquid levels, keep within designated ranges to ensure effective separation and prevent carryover. Control and shutdown parameters. 1. High pressure shutdown, PSD pressure safety device. Trigger, high pressure set point exceeded. Action, shut down the inlet flow and activate emergency pressure relief. 2. High level shutdown, level safety device. Trigger, high liquid level set point exceeded. Shut down the inlet flow and open drain valves to prevent overflow. 3. Emergency shutdown, ES trigger, manual activation or detection of critical fault conditions, e.g. fire, gas leak. Action, shut down all inlet and outlet flows, activate emergency pressure relief systems, and isolate the slug catcher. Maintenance and best practices. 1. Regular inspections. Frequency, daily visual inspections and monthly detailed inspections. Focus, check for signs of wear, corrosion, leaks, and blockages. 2. Calibration and testing. Frequency, quarterly calibration of instrumentation and control devices. Focus, ensure accurate measurements and reliable control loop performance. 3. Cleaning and deslugging. Frequency, periodically, based on operating conditions and slugging frequency. Focus, remove accumulated slugs and debris to maintain separation efficiency. 4. Valve and instrumentation maintenance. Frequency, as per manufacturer's recommendations and based on operational history. Focus, ensure all control valves and instrumentation are functioning correctly. 5. Safety checks and drills. Frequency, biannual safety system checks and emergency drills. Focus, verify the functionality of shutdown systems and train personnel on emergency procedures. 6. Data analysis and optimization. Continuous data monitoring with periodic reviews. Focus, analyze operational data to identify trends and optimize slug catcher performance. Practical examples and solutions. 1. Issue, high pressure surges. Cause, sudden influx of gas due to upstream operations. Solution: implement robust pressure control loops with quick-acting pressure relief valves. Issue: inadequate separation. Cause: high liquid levels leading to carryover. Solution: regularly calibrate level transmitters and ensure proper functioning of level control valves. 3. Issue: instrumentation failure. Cause: harsh operating conditions causing sensor drift or failure. Solution: use high-quality, ruggedized sensors and implement a proactive maintenance schedule. 4. Slugging and blockages. Accumulation of slugs and debris in the separation section. Solution: regular cleaning and deslugging operations, coupled with efficient inlet flow control. 5. Issue: ineffective emergency shutdown. Cause: faulty ESD systems or delayed response. Solution: conduct regular testing and drills to ensure ESD systems are functional and personnel are well trained. Conclusion: effective monitoring and control of a slug catcher in an onshore oil facility require robust design and implementation of control loops, regular maintenance, and proactive operational strategies. By addressing potential issues and adhering to best practices, the slug catcher can operate efficiently, ensuring smooth downstream processing and protecting valuable equipment from damage. Correlation of control aspects and implementation of feed-forward and feedback control loops. To manage operations of a slug catcher in steady state without the need for frequent operator intervention or resorting to emergency shutdown systems, ESD, both feed-forward and feedback control strategies can be integrated. This ensures the process remains within safe operational parameters, efficiently handling variations in incoming flow and composition. Feed-forward control loops. Feed-forward control loops anticipate changes in the process by measuring disturbances and making preemptive adjustments to maintain steady-state operations. These loops are particularly effective in handling predictable changes or disturbances that can be measured before they affect the system. 1. Inlet flow. Feed-forward control. FFIC, feed-forward flow indication control. Objective: adjust the operation of the slug catcher based on anticipated changes in inlet flow from the well clusters. Mechanism: measure the flow rates from individual well clusters and calculate the combined flow rate entering the slug catcher. Adjust the inlet control valves accordingly to prevent overloading. Example: if an increase in flow is detected from multiple well clusters, the inlet valves can be adjusted to manage the total incoming flow rate, ensuring the slug catcher operates within its capacity. 2. Gas pressure feed-forward control, FFPIC, feed-forward pressure indication control. Objective: preemptively manage gas pressure within the slug catcher based on upstream pressure changes. Mechanism: measure upstream pressures and anticipate their impact on the slug catcher. Adjust the gas outlet control valves and pressure relief systems accordingly. Example: if an increase in upstream pressure is detected, the gas outlet valves can be opened slightly in advance to manage the increased gas flow and prevent pressure surges within the slug catcher. 3. Liquid level feed-forward control, FFLIC, feed-forward level indication control. Objective: adjust liquid handling based on anticipated changes in liquid flow rates. Mechanism: measure incoming liquid flow rates and adjust the liquid outlet control valves to manage the liquid levels within the slug catcher. Example: if a spike in liquid flow is detected, the liquid outlet valves can be opened to handle the increased volume, preventing overflow and ensuring effective separation. Feedback control loops. Feedback control loops respond to deviations in the process by measuring the output and making corrective adjustments. These loops ensure the process remains within desired operational parameters by continuously monitoring key variables. 1. Inlet flow feedback control, FICE, flow indication control. Objective: maintain a steady flow rate into the slug catcher. Mechanism: use flow meters to continuously measure the incoming flow rate and adjust the inlet control valves based on real-time flow data. Example: if the flow rate exceeds the set point, the inlet valves are automatically adjusted to reduce the incoming flow, ensuring the slug catcher operates within its design capacity. 2. Gas pressure feedback control, pressure indication control. Objective: maintain the gas pressure within safe limits. Mechanism: Use pressure transmitters to monitor the gas pressure within the slug catcher and adjust the gas outlet control valves and pressure relief systems as needed. Example: if the pressure rises above the set point, the gas outlet valves are open to release excess gas, maintaining the pressure within safe operating limits. 3. Liquid level feedback control, LIC, level indication control. Objective: maintain the liquid level within the designated range. Mechanism: use level transmitters to monitor the liquid level within the slug catcher and adjust the liquid outlet control valves accordingly. Example: if the liquid level rises above the set point, the liquid outlet valves are open to drain excess liquid, ensuring effective separation and preventing overflow. Integrated control strategy. To achieve steady-state operations without the need for operator intervention or emergency shutdown, an integrated control strategy combining feed-forward and feedback loops is essential. This strategy ensures proactive management of disturbances and reactive adjustments to maintain process stability. 1. Feed-forward and feedback inlet flow control. Combined approach. Use feed-forward control to anticipate changes in incoming flow and make preemptive adjustments, while feedback control continuously monitors and fine-tunes the flow rate. Implementation. Install flow meters at each well cluster and at the inlet of the slug catcher. Use a feed-forward controller to adjust the inlet valves based on the combined flow rate from well clusters, and a feedback controller to fine-tune the inlet valves based on real-time inlet flow data. 2. Feed-forward and feedback gas pressure control. Combined approach. Use feed-forward control to anticipate pressure changes and preemptively adjust gas outlet valves, while feedback control continuously monitors and maintains the gas pressure within safe limits. Implementation. Install pressure transmitters upstream and within the slug catcher. Use a feed-forward controller to adjust gas outlet valves based on upstream pressure changes, and a feedback controller to fine-tune the gas outlet valves based on real-time pressure data. 3. Feed-forward and feedback liquid level control. Combined approach. Use feed-forward control to anticipate changes in liquid flow and adjust outlet valves preemptively, while feedback control continuously monitors and maintains liquid levels within the designated range. Implementation. Install flow meters at the inlet and level transmitters within the slug catcher. Use a feed-forward controller to adjust liquid outlet valves based on anticipated liquid flow changes, and a feedback controller to fine-tune the liquid outlet valves based on real-time level data. Best practices for implementation. 1. Robust instrumentation. Ensure high-quality, reliable sensors and transmitters for accurate measurement and control. Regularly calibrate and maintain instrumentation to ensure accuracy. 2. Redundancy and backup systems. Implement redundant control loops and backup systems to ensure continuous operation in case of a primary control loop failure. Install backup power supplies for critical control systems to ensure uninterrupted operation during power outages. 3. Advanced control algorithms. Utilize advanced control algorithms and predictive analytics to enhance the performance of feed-forward and feedback loops. Implement adaptive control strategies that adjust control parameters based on changing process conditions. 4. Comprehensive monitoring and data analysis. Continuously monitor key process parameters and analyze data to identify trends and potential issues. Use data analysis to optimize control strategies and improve process stability. 5. Operator training and automation. Train operators on the integrated control strategy and the use of automated control systems. Implement automation to reduce the need for manual intervention and ensure consistent, reliable operation. Conclusion. By integrating feed-forward and feedback control loops, onshore oil facilities can achieve steady-state operations of slug catchers with minimal operator intervention and reduced reliance on emergency shutdown systems. This integrated approach ensures proactive management of disturbances and continuous fine-tuning of process parameters, enhancing the stability, efficiency, and safety of the slug catcher operation. Advanced control algorithms for slug catcher control. To enhance the performance and stability of slug catchers, advanced control algorithms such as model predictive control, MPC, adaptive control, and cascade control can be implemented. These algorithms offer sophisticated methods for handling the dynamic and often nonlinear nature of slug catcher operations. Number 1. Model Predictive Control, MPC. Overview. MPC uses a model of the process to predict future behavior and optimize control actions. It is well suited for handling multivariable systems with constraints. Implementation. Process model. Develop a dynamic model of the slug catcher that includes interactions between flow rates, pressures, and levels. Prediction horizon. Define a prediction horizon over which the controller predicts future process behavior. Optimization. At each control step, solve an optimization problem to determine the best control actions that minimize a cost function while respecting constraints. Control actions. Implement the first control action from the optimized sequence and repeat the process at the next control step. Practical example. Application. Use MPC to control the liquid levels and gas pressure in the slug catcher. Advantages. MPC can handle multiple inputs and outputs simultaneously, predict future disturbances, and optimize control actions to maintain stable operations. Implementation steps. 1. Develop a dynamic model of the slug catcher that captures the relationships between inlet flow rates, liquid levels, and gas pressure. 2. Define a prediction horizon and an optimization problem to minimize deviations from set points while respecting operational constraints. 3. Use real-time measurements of flow rates, levels, and pressure as inputs to the MPC algorithm. 4. Implement the calculated control actions for inlet valves, gas outlet valves, and liquid outlet valves. 2. Adaptive control. Overview. Adaptive control adjusts controller parameters in real time based on changes in process dynamics. It is useful for systems with time-varying or uncertain dynamics. Implementation. Parameter estimation. Continuously estimate the process parameters using real-time data. Controller adjustment. Adjust the controller parameters based on the estimated process parameters to maintain optimal performance. Self-tuning. Implement self-tuning mechanisms to automatically update control parameters. Practical example. Application. Adaptive control for maintaining the liquid level in the slug catcher. Advantages. Automatically adjusts to changes in process dynamics, ensuring robust performance under varying operating conditions. Implementation steps. 1. Implement a parameter estimation algorithm to continuously update the model parameters based on real-time level measurements. 2. Adjust the level controller parameters, e.g. PID gains, based on the estimated model parameters. 3. Use self-tuning mechanisms to ensure the controller adapts to changing process conditions. 3. Cascade control. Overview. Cascade control uses a hierarchy of controllers to improve control performance. A primary controller regulates the main process variable, while a secondary controller regulates an intermediate variable. Implementation. Primary controller controls the main process variable, e.g. liquid level in the slug catcher. Secondary controller controls an intermediate variable, e.g. flow rate to the liquid outlet. Inner and outer loops. The secondary controller forms the inner loop, and the primary controller forms the outer loop. Practical example. Application. Cascade control for maintaining the liquid level using flow rate control as an intermediate variable. Advantages. Improved disturbance rejection and faster response to changes in process conditions. Implementation steps. 1. Implement a secondary flow controller to regulate the flow rate to the liquid outlet. 2. Implement a primary level controller to regulate the liquid level in the slug catcher. 3. The output of the primary level controller adjusts the set point of the secondary flow controller. 4. The secondary flow controller adjusts the liquid outlet valve to achieve the desired flow rate. Example implementation. Scenario. Controlling the liquid level and gas pressure in a slug catcher using MPC, adaptive control, and cascade control. Control objectives. Maintain the liquid level within a specified range to ensure effective separation. Maintain the gas pressure within safe operating limits. Control strategy. 1. Model predictive control for gas pressure. Develop a dynamic model of the gas pressure system. Use MPC to predict future gas pressure and adjust gas outlet valves to maintain pressure within limits. 2. Adaptive control for liquid level. Implement a parameter estimation algorithm to continuously update the model parameters based on real-time level measurements. Adjust the level controller parameters based on the estimated model parameters. 3. Cascade control for liquid level using flow rate. Implement a secondary flow controller to regulate the flow rate to the liquid outlet. Implement a primary level controller to regulate the liquid level in the slug catcher. The primary level controller adjusts the set point of the secondary flow controller, which then adjusts the liquid outlet valve. Example control loops. 1. MPC loop for gas pressure. Input, gas pressure measurements, upstream pressure changes. Output, control signals for gas outlet valves. Optimization, minimize deviations from pressure set point while respecting constraints. 2. Adaptive control loop for liquid level. Input, liquid level measurements. Output, adjusted PID controller parameters for the level controller. Parameter estimation, continuous update of model parameters. 3. Cascade control loop for liquid level. Primary loop, level control. Input, liquid level measurements. Output, set point for the flow controller. Secondary loop, flow control. Input, flow rate measurements to the liquid outlet. Output, control signals for the liquid outlet valve. Best practices for implementation. 1. Model accuracy. Ensure the dynamic model used for MPC accurately represents the slug catcher system. Regularly update the model parameters to reflect changes in process conditions. 2. Real-time data. Use reliable sensors and transmitters for accurate real-time measurements. Implement data validation and filtering techniques to ensure the quality of input data. 3. Robust algorithms. Use robust control algorithms that can handle process uncertainties and disturbances. Implement fallback strategies to handle sensor failures or communication issues. 4. Continuous monitoring. Continuously monitor the performance of control loops and adjust parameters as needed. Use data analysis tools to identify trends and optimize control strategies. 5. Operator training. Train operators on the use of advanced control systems and automated control strategies. Provide clear guidelines for manual intervention in case of control system failures. Conclusion. Implementing advanced control algorithms such as MPC, adaptive control, and cascade control can significantly enhance the performance and stability of slug catcher operations in an onshore oil facility. By combining these algorithms with robust instrumentation and continuous monitoring, the process can be managed effectively in steady-state conditions, reducing the need for operator intervention and minimizing the risk of emergency shutdowns.